So free mind is a devil's workshop. Which of these two are free and not doing anything? Bond pair or the lone pair?
Lone pair.
Its lone pair is not doing anything, it's not bonded. Now think which of them will interact more or fight more. A lone pair, or the lone pair, bond pair. So the lone pair and lone pair which are not bonded are going to interact more because it's free, it's not bonded. So this is like, it's like an untrained dog. It's like a trained dog, something like that. They are more likely to fight. So you would want to keep these untrained dogs, which are the lone pairs, who are more likely to fight farther away than you would keep more two dogs which are trained together. Okay? But in general, you would want to keep them away. Now let's imagine a simple case in which you have a post in here and you want to keep two dogs. How would you place, and it's like, this is like a post, okay, and two dogs are tied to a stick. Let's call this M for some reason, and let's call these, I don't know, X for some reason. So this is the dog, this is this post. Where would you keep the other dog? You have to keep it farthest apart. Where would you keep them? Because they're going to fight, we just want to put them as separate as possible. Where would you keep them? Very intuitive, don't think about chemistry. Just think, where would you just place them so that they have the least chances of interacting? Just on the opposite end, right? Sometimes my questions are very easy so that no one answers, right? So what's the angle between these two things? 180, right? And what's the shape of this thing? If you're just seeing the shape, okay, I can see that dog, I can see this M middle post, and there I can see another dog. So what's the shape that that thing is making? Linear. Okay, now let's make it a little complicated with three dogs. Where would you keep them? How would you arrange them?
Kind of whatever 360 three-way is, so that.
Yep. What's the shape that you can see? If you can just see the dogs, you cannot see. So what's the shape that you are seeing? A triangle, right? And it's a planar triangle. Planar means it's on the same plane. You don't have to put it on a different. So it's a planar, trigonal planar is the term that we will use. Everyone agrees it's a trigonal planar? See, I was not going to teach these things, but you guys did so well in your PS1 that I'm like more inclined to teach these things and make it a little more enjoyable. Other word for harder, right? So trigonal planar. 4 dogs.
Basically make a square.
Square. But here comes the trick. You can use the space. So you are in
A
tetrahedral. And Brian, what's a tetrahedral shape? Can you explain it to me? It's a very simple thing.
Yeah, it's basically a pyramid with one dead center in the center. So you're going to have one to the north and then 3. I always do the pyramid with whatever you want in the middle.
So the thing that you see, is it a pyramid? The tetrahedral. So why don't we call it a pyramid?
Because pyramid has 4 sides. Sorry.
No. Don't be. Pyramid can be of many different kinds. Pyramid is a very generic term that we use. We'll see. But I just want you to tell me, and the class, how do you visualize a pyramid? this tetrahedral shape, because it's very critical in organic geochemistry.
I literally only think of quartz. It sounds stupid, but when I think of the tetrahedron,
Quartz too, yeah. Quartz also has this, yeah. But what's that shape? How do you, when you think about quartz, what do you think?
the tetrahedron, like, I mean,
Okay, yes, Tiffany. It has faces on it, yes. You're right. So it's a 3D, first of all. It's not planar, it's a 3D structure. See, this is, Courtney, do you imagine tetrahedral in any other way? No. Okay, let me give you how I imagine it, and it works for me. So, I start with a pyramid. So, think like, it's a weird pyramid. So let's imagine you're visualizing the pyramids of Egypt. Okay, you can see this like the top. Okay, now the pyramids of Egypt, if you look at from above, you can see that the base is a square. So that pyramid that you see in Egypt is a square pyramidal shape. That's what that is, because the square is just telling you that when you see it from top, how many sides are there. So you can also have a pentagonal pyramid shape. What if like I want to draw a pentagon and just draw a pyramid? I can also have a hexagon, it never ends. What I drew here is a trigonal pyramid. Okay, just one step back, because who is stopping me from doing anything? I am a professor. I can do anything. Not anything. But so the thing is, just imagine like this is not like a normal pyramid shape. It's like, so the back is coming like this. So when you see it from top, you're seeing like a triangle. Okay. Now, I will place one of the dogs here, here, and here. And then I will place one dog up here. Okay? Now I will make these dotted. Now the structure that you see with the apex of the pyramid inside of that structure, with the 4 dogs, in 3 in this, on this plane, and 1 on that top, is kind of what I visualize. It's not exactly, but this is kind of what I visualize for a tetrahedral shape. You cannot see the M, right? So when you're looking at a tetrahedral, this inside one is just inside of that. So for quartz, the silica would be like in the inside. You won't be able to see that. You can only see the O's going out, and this is what I visualize. So you cannot see so that the structure which you can see, that structure is called tetrahedral. Or a regular tetrahedron is the thing. Shape is tetrahedral. So regular, this is a regular tetrahedron. What's the angle?
90 degrees.
Sorry?
90 degrees.
They're not 90 degrees.
Oh, we should get all
No, they're not. They're 109 degrees 28 minutes. Okay? I will just skip how we got 109 degree 28 minutes because I don't know and just tell that I know, and I don't know. I mean, I can find it out, but for our purposes, I'll just say that it's not required. If I knew, I would have told you. Okay, so 109. I'm sure this. I'm sure this will. This is correct. But this is the shape. So all these angles are 109 degrees 28 minutes. That is what makes it a regular tetrahedron. If some angles are a little less than 109, some are a little more than 109, that will not be a regular. So regular is the word used in which all these angles between this and this, this and this, this and this, and all these angles are 109 degrees 28 minutes. For quartz, it will hold true. It's like a regular tetrahedron. And for many cases, for methane, it will hold true, and we'll see that how. Okay? So this is like the regular tetrahedron. For 5, I'll just tell because it's difficult to guess. The thing is, for 5,
Below, right?
we'll have one below, but we'll make it, now, 109 degrees 28 minutes means they're getting closer. Right, so it's closer than 120 degrees. So if I just put one down, then all these things are not in a plane. Right? So if you're putting it, because these 3 are not in that, because if these were in a normal plane, the 109 would not hold. So when I told you to visualize these, there's a trick, like they're not sitting on the same plane. That's how I start explaining you things, so that doesn't get complicated. But in actuality, these are not on the same plane. They're like slightly distorted from that plane, so that 109 degree 28 minutes is maintained. Because if these were on the same plane, 2 of them are on the same plane, and one of them is like kind of like outside the plane. Okay, we'll come to this, in which 2 of them can be on the same, one comes out and one goes back to use that entire space. So whenever you see a methane molecule, you draw it something like this, right? So these 2 are these 3 are on the same plane. This one, the wedge, is coming towards you. Just imagine if this is the bond, so these bonds are on the plane. So it's this bond is kind of like doing this thing. It's like coming towards you, and this bond is doing the opposite and going back. Right? I could not have started out with this. You will be really confused, but this is not on the same plane. So getting it behind is not going to work. But yeah, it will work in some cases. We'll see. What the next, when you have 5 dogs to cater to, what you do is you make a triangle with M in between, and these X, 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 and then you do this. So imagine there is a triangle on this plane, and there's one thing is coming up and one thing is going down. So when you're seeing from the above, you can see a triangle. One of the bonds is coming this way and one of them is going that way. Now, the important thing is, what are the angles? For the triangle, what the angles are? So if you are looking at flat on top like this, you can see this, right? What are the angles? These? It's 120. 120, right? So 360, so it's 120. So these angles that you have between these 2 bonds, which are lying on the plane, are 120s. Okay, we call that plane the equatorial plane. Let's call that equatorial plane. So this plane, let's call this equatorial. So the bonds will be equatorial bonds. This is like kind of like an axis. So like a thing that is coming out like this from this plane. So what's the angle that is this bond is making with the plane? 90 degrees, right? Yeah, I mean, not the entire, yeah. It's 90 degrees. So these angles are 90 degrees. So now things are getting complicated, because now not all the angles are equal. Some angles are 120 degrees, some angles are 90 degrees. Hunter, can you visualize this?
Yeah, I'm trying to understand the importance of the angles.
Yes.
How does that,
Let's,
like in a real world application,
so
it's
let's,
an ignorant question, but
no, it's not an ignorant question. It's a very important question. Because let's compare these two. Which of these bonds are interacting more? The bonds which are separated 180 degrees or bonds which are separated 120 degrees? This versus this, which is interacting more? Which dog is interacting more with the other one?
I guess we're treating it.
The 120 is more because it's closer. So what if you make it 90?
It's closer.
It's even closer. So in this case, if these bonds are closer, they're interacting more, and these are both electrons, right? So electron pairs interacting with electrons, is that a stabilizing effect or a destabilizing effect? It's a destabilizing effect because electrons are going to repel these electrons, the other ones. So the repulsion is going to destabilize it. So generally, this structure is more stable than this, because there are less interaction between. So if you have this interaction is more, this interaction is less. So now, oh, I love this. Equatorial bonds are, like, let me put this question up. Which bonds are longer? The equatorial bonds or the axial bonds? Now just skipped a thing and just went to the length, because what controls the length? The stability, right? So things that are more stable will be shorter, and the things that are less stable will be longer. Now tell me which is the longer bond?
Single bond.
No, all are single. No, all are single.
The equatorial bonds?
Who says equatorial bonds? Who thinks equatorial bond is the answer? I don't know the answer. Let's find it out. Like, let's talk us through what you're thinking.
I mean, I figured because it's 120 degrees,
Yeah,
so it should be a wider angle than 90.
that's true.
So the bond length would be longer.
No, don't skip it. So when you have 120 degrees, which is more than 90 degrees, right? So the 120 degrees are more stable, more energetic, or less energetic?
More energetic.
Why they're more energetic? Because they are more farther apart.
Less energetic.
It'd be less
There is-
stable, right?
No, it'd be more stable,
Okay.
so less energetic.
You don't have to be convinced until you are. Are you convinced? I don't think so. You're convinced.
So
He's right, but are you
you
convinced?
mentioned that the shorter the distance, the
Yeah.
more stable.
No.
Oh, the less stable.
Why? No.
The
If
electricals.
yeah,
Yeah,
right.
that's right.
I mean, if there were opposite charges, then getting closer would have stabilized them. But they're same charges, or getting them together are going to repel them. So in this case, getting closer. So don't think like getting closer is always stabilized. No, don't think about that. Maybe that is for some scenario, but for this, the electrons are getting closer, making it more energetic, less stable, right? So 120-degree bonds, which are on the equator, which are equatorial bonds, are going to be shorter and more stable than the axial. So the axial bonds are longer, less stable. Equatorial bonds are shorter and more stable because of the angle. This is the first time out of all these where the bond lengths are different. So in this case, this was equal to this was equal, all of them are equal. For the first time in here, the bond lengths are getting different. What would you call this shape? Brian, shape expert. Give me a name for this shape. So just think, you have a triangle, and it's like a, what's this? When you have any shape and you do this, what's that? It's a pyramid.
Yeah,
Convinced?
yeah.
So what's this shape?
Triangle gradient.
So it's a trigonal pyramid, but how many pyramids are there?
So bi-pyramid.
So it's a trigonal bipyramidal structure. Right. So it's a trigonal because of the base by
If you have like a double bond, would that affect anything?
let's not go to double bonds. In general, because like double bond will complicate things in their own special way. But yeah, it will if you have a double bond, if you have. Okay. What about 6? 6 is easier than 5. Just let me tell you this. If you have 6 dogs, 6. So now let's move from the dogs to actually. So this is like the central atom and the bonds that you're making with the atoms that are coming to bond, right? Central atom, and then what do you call those? We can call them ligands if like, but this surrounding atoms, whatever. 6, like you have 6 now. It's simple. Go from this now. Like it will look similar to this, but what would you do from that triangle? Just make it a square. So what will be the shape now for 6?
Square.
Bipyramidal.
Square bipyramidal. Right. And that thing is called an octahedron. You must have heard about this term, octahedron. But that is just a square, because when you see, it's the base looks like a square, and you put one in and put one down. Now you tell me what's going to be the axial versus the equatorial, which is going to be longer?
Access, 'cause it's going.
Think now, think about it.
Isn't everything 90 degrees, something like that?
Exactly. So all angles now are 90 degrees. So now, so this is the square, you have one here and one here. So these insides are also 90 degrees. And this is also a 90 degree. Right? So when you have 6, all these are, so one is here, here, and one is down. So this is a square bipyramidal, and this is also called an octahedron. What does octa mean?
8.
Did we make a mistake by calling it an octahedron? It should be hexahedron. Why octa?
Because they're mean.
Because
They're mean.
that could be it. Yes,
There's 8 faces.
exactly. There are 8 faces. So the faces are getting more importance than the vertices. So they have 6 vertices but 8 faces. So that's how they got the term octahedron. I was not present there when we were doing these things, but yeah, okay. And I don't really understand these things that much, but yeah, octahedron. So this, all the angles are going to be same. So this is called like a regular octahedron, but this is not. This is, okay, a regular octahedron, regular tetrahedron. And for tetrahedron, there are like 4 faces. Right? It's not a very easy thing, but just remember a pyramid with a stick on top. That's generally it. And the pyramid's apex is like hidden inside. What happens when you have, so this was 6. What happens when you have 7?
A T-shape or something like that.
Oh, no. So, don't do that. Come back here. 7. Well,
Isn't it like 6, but it's like 1?
you have 7. So when you went from this to this, you just increased like one more in the base. Just do that. So you went from a trigonal bipyramidal to a square bipyramidal. What's the next step?
You can't do a pentagonal, can you?
You can.
Pentagonal base?
Yeah.
Okay.
It's a pentagonal. The thing that you're thinking about the pentagon is like the symmetry thing, in which the 5 things of the, that's not this, that's a different thing. So what Venus is talking about is, when we'll talk about, if you have taken mineralogy, you have seen that when you have like forming these lattices or like the repeatable structures, you can have a 2 repeat, like a repeats, or a 3 or a 4 repeats, but you don't have a 5, then you can have a 6 and an 8, things like that. That's not this. So this is like a simple pentagonal bipyramidal. Now, the angles, tell me the angles and the lengths, which is going to be a longer, shorter, whatever.
Angles, 120.
So insides, what's the angle? So 360 by 5, right? What's this? I'm not going to do the math. I am not going to do the math.
It's like 71.
72, right? And what's this? Like the actual? It's still 90. So what about the stability? Which becomes like the stable, the axial or the equatorial? Which is a more stabler position, the axial or the equatorial?
The equatorial?
The equatorials, so the bond angles of equatorials are like 72, and in here it's 90.
Yeah.
Which one of them are closer? 72s are closer. It's going to be more energetic, less stable. So in this case, the equatorial bonds are longer and less stable. The axial bonds are more stable and shorter.